Hi everyone, this is the video lesson for 5.5, the derivative of y equal to 10x, part 3. If you haven't watched part 1 or part 2, make sure you go back and watch it before continuing with part 3. Example number 3. Again, this is from your textbook, question number 6 on page 260. Determine the local maximum point on the curve y equal to 2x minus 10x, where x is in between negative pi over 2 and pi over 2. Step 1. The fact that y equals to 2x minus 10x, you can find the derivative. So y prime equals to 2 minus secant square x. You're going to set this to 0, and you have to find the critical points. When you bring negative secant square x to the left, that's going to be positive secant square x, which equals to 2. By definition, secant square x is 1 over cosine square x, which equals to 2 divided by 1. You can cross multiply, you can take the reciprocal, so cosine square x equals to half. Don't forget, when you find the square root of both sides, there are two cases, plus and minus the square root of 1 over 2. Now I'm going to continue here, and you want to really be mindful that there are two cases that you're thinking about. So in the first column, I'm going to look at the positive case. So cosine x equals to 1 over root 2. And in the second column, which I'll come back to, of course, cosine x is going to be negative 1 over root 2. Now, this really goes back to grade 11/grade 12 math. And again, some of you recognize the answers just by looking at it. Others will draw this diagram. Don't forget C, A, S, T. The fact that cosine is positive, you're focusing specifically on quadrants 1 and 4. Cosine by definition is going to be opposite over, not opposite. Cosine by definition is going to be adjacent over hypotenuse, so 1 over root 2. Likewise, 1 over root 2 like that. You should recognize this is the second special triangle, so this is 1 and negative 1, because down is negative 1. And the angles are going to be pi over 4 respectively. Now be careful here, because the values you're looking for, it's in between negative pi over 2 and positive pi over 2. So in the first case, there's going to be one angle right there. And the second angle is going to be right there. Again, think about the domain. Don't just randomly do this. So x equals to pi divided by 4 or negative pi divided by 4. And I'll put a box around this in the first case. Now likewise, if you look at the second column, cosine x is going to be negative 1 over root 2 this time. So again, if you want to draw the same diagram and you think about the negative cases, C, A, S, and T, the fact that cosine is negative, you're now focusing on quadrants 2 and 3. Let's try this again. 2 and 3. Now again, the angles are going to be pi over 4, because adjacent over hypotenuse is negative 1 over root 2. And again, I hope you recognize it's the second special triangle. There are two angles you're focusing on, but again, you're thinking about the angles specifically between negative pi over 2 and positive pi over 2. So the problem is, when you first look at this, you may think that x equals to 3 pi over 4. You might even think 5 pi over 4. And that's this one. But remember, that's not within the domain. So these numbers, even though mathematically it works, but it's not the final answer because they're rejected, they're not part of the domain that they're asking for. And the only number that works is going to be from the first case. So even if you look at this last case, let me just point that out quickly, even this one, right? If we went clockwise, which would give you negative 3 pi over 4, Again, for the same reasoning that's beyond the domain, so there are really no solutions here. And again, that's perfectly okay. The answer is there's no answer. So the only correct final answer, based on in both cases, is plus and minus pi over 4. So I'm going to write this again in a box. So the summary is, therefore, x equals to plus and minus pi over 4. Now remember, the question is asking you for the local maximum point. So what you're doing is you're comparing them. And again, let's compare it here. Now, if you compare negative pi over 4 with positive pi over 4, again, you're going to plug it back to the original function, which is 2x minus 10x. That's going to be 2 times negative pi over 4 minus 10 times negative pi over 4. Again, you can take the calculator, work it out to the nearest decimal. That's going to be negative 0.6. Likewise, if you plug in positive pi divided by 4, and when you work this out, again, make sure you're in radian mode when you're doing this. This will give you approximately 0.6. So the larger number is the second case, which means therefore the local maximum is located at pi divided by 4, 0.6, or if you want to put this both in decimals to the nearest tenth, that's going to be 0.8, 0.6, just like that. One more time, example number 4. This is number 7 from your textbook on page 260. Prove that y equal to secant x plus tan x. It's always increasing on the interval. X is in between negative pi over 2 and positive pi over 2. Again, I would like you to press pause. Try this for 5 minutes. When you press play again, I'll be right here. Okay, let's take a look. Now, if you want to translate this, always increasing, this means the derivative, it's going to be positive, and we'll get to that in a moment. Again, here's the first step. Y equals to secant x plus tan x. Y prime equals to secant x tan x plus secant square x. And again, it goes to find increasing, decreasing, but if you take the common factor of secant x to the front in brackets, this will give you tan x plus secant x. You can rewrite this in terms of sine and cosine. Y prime is going to be 1 over cosine times x, and in brackets, it's going to be sine x over cosine x plus 1 over cosine x. And again, if you combine all this as one fraction, y prime is going to be sine x plus 1 divided by cosine square x. So notice the common denominator, cosine x times the cosine x at the front. Now, you want to show that this is always increasing. So a couple of things you should notice right off the bat. If you look at this bottom part, you know cosine square x, it's always going to be positive. Cosine square x, it's always going to be positive. So if you want to make sure that this is positive, you got to look at the top, right? And again, likewise, sine x plus 1, it's always positive. So therefore, the derivative, it's always positive in between negative pi over 2 and pi over 2. And again, I want to show a diagram to justify this. When I say it's positive, I'm not saying this is positive in all space. I'm saying the numerator and the denominator are both positive when x is in between negative pi over 2 and positive pi over 2. And if you draw a diagram, it looks roughly something like this. So let's set up a scale, negative, positive pi over 2, and roughly something like that. Now, again, this is negative pi over 2. That's positive pi over 2. And if I sketch a diagram, we don't include the endpoints. Notice how it's increasing. There's some concavity happening. Y equals to sine x plus 1. So this is not the graph in terms of the original function, but in terms of this part, I just want to show that when I say y equal to sine x plus 1 is always positive, I'm just referring for that specific domain, not in all space, just like that. Now again, before you try the homework number 1 to 11 on page 260, I want to practice this one more time with you. And if you take a piece of paper and you write this down 3 times, and you do this pretty much every day within about a week, you will know this by heart. So let's finish strong. I'm going back to what we kind of started from the previous video. So here are the 6 cases again, and I'm going to kind of circle back to the basics. So I'm saying that the derivative of sine x equals to cosine x. The derivative of cosine x equals to negative sine x. The derivative of tan x equals to secant square x. The derivative of cosecant x equals to negative cotangent x cosecant x. The derivative of secant x equals to secant x times tan x. Last but not least, the derivative of cotangent x is going to be negative cosecant square x. I hope this makes sense.